For those of you who don't know me, I'm Bill Wilson. I'm the executive director for the Center for Nanoscale Systems here at Harvard, and I'm one of the organizers for this meeting, Quantum Noir. It was actually, I'll tell the story of how the genesis of this meeting probably tomorrow. But today is the tutorial day, and the idea here is to give everybody kind of a basic grounding of kind of the phase space of all the things we'll be talking about over the next 3 days. I apologize in advance if the level is too low for you, in part because this is the first time we've done this and we're not sure where to start, right? So we targeted most of the talks and a lot of the tutorials to kind of advanced undergraduates and graduate students, right? Just to get that focus going. But I'm sure everyone will be more than willing to answer questions that are beyond that. And so I hope you do that tomorrow. So there are 3 talks today. The first talk will be given by Nishant Sule. And Nishant, for those of you who are looking to go to graduate school, is the Director of Education and Scientific Outreach for the Harvard Quantum Initiative. The Harvard Quantum Initiative is kind of the budding seeds of Harvard creating a quantum engineering department, right? And so we're taking students in that are focused exclusively on quantum science and engineering. And Nishant is literally part of the founding team of that department. And in the end, he will probably be the chair of the committee for admissions. And so you should be nice to Nishant. The second, and he's going to give you kind of an introduction to quantum computing, kind of ranging from qubits to gates and logic. The second talk will be given by a new professor, Julia Semignani, and she's an associate professor in applied physics. She actually worked originally in Misha Lukin's group using neutral atom platforms to do quantum computation and quantum simulation. She'll give our second talk, exploring different paradigms for doing quantum computation. And then the last talk will be given by Dr. Neil Sinclair, who is a research scientist who works with Marco Loncar on quantum networking. But he also has the benefit that Neil has his hands in most of the quantum networking activity that's going on across the country. He has a foothold in Caltech, a foothold at University of Calgary, a foothold in Fermilab, and he's been heavily involved in the new quantum network demonstration platforms that have been set up both here in Chicago and in the Boston area. And so he'll give the third talk in this series. The talks will be nominally an hour with ample time for questions. You probably can't see this. If you actually have already downloaded the app, the schedule is already out for the rest of the week, but we will post it on a poster, so it will be around, but you can get to it on the app. We will start again tomorrow morning at 8:30 a.m. With some remarks from David Parks, our new Dean of Engineering, and Munji Bawendi, who actually ended up being summoned to Tunisia to get an award from the Tunisian parliament. So he recorded a video for us tomorrow. For those of you who don't know, Munji Bawendi just won the Nobel Prize in chemistry. So what do I want you guys to get out of this week? The most important thing about this week is I really do want you guys to build connections. I tell the students all the time that science is a contact sport, right? You navigate your way on your scientific path by interacting and collaborating and joining together and learning from other scientists. And this is an opportunity for you to start to build that cohort. But we will have young faculty here. We will have folks from industry here. We'll have folks from the venture sector here. And so you'll get a pretty wide view of kind of what the cross-section of what quantum science and engineering looks like today and where a good number of folks think it's going. And then last but not least, I'll give you a few housekeeping things. I'll probably have more for you tomorrow. As I mentioned, the breakfast will start up in the physics library again at 7:30 tomorrow. We will definitely want to do a conference picture. I think we can sneak it in before lunch tomorrow, and so that would be the goal. And that'll just happen right here out in front of Jefferson on the steps. And then last but not least, though we haven't figured out how we're going to do it yet, I think we're going to have a virtual job board. And I think the app already supports that, but only Damien knows how to use the app. And so I think we'll all figure it out tonight and let you know tomorrow. And so with that, I will get out of the way and hand over the floor to Nishant.
It should be. Thank you, Bill, for such a kind introduction. While I set up my computer, I'll perhaps echo something that Bill said. I apologize in advance if this is too basic of a level, but my intention was really to make sure that everyone, no matter what area you're coming in from, hopefully gets something out of this tutorial. So let's see. I think this clicker should work. All right. So with that, let me just dive right into it. So everyone is here. This is a conference about quantum. You all have noticed quantum computing seems to be everywhere, right? This is a Google Ngram for the term quantum computing. The Google Ngram basically counts the number of times a term appears in the corpus of literature. And you notice that not only has quantum computing grown exponentially, and now granted that I'm cheating a bit. I have my axis starting from the 1900s, which is kind of when quantum theory was invented. But not only is it everywhere, it seems to be everywhere all at once. There's like an exponential increase in the number of times quantum computing appears in the last 10 years or so. And this is, evident if you read any kind of newspaper. You must have seen articles that talk about how quantum computing is going to revolutionize X, Y, and Z. These articles appear in newspapers or websites targeting the broad public, from 60 Minutes in CBS, CNN Business, US Money, telling you which quantum computing stocks to buy, all those things. But nothing really takes home this message that quantum computing is everywhere, more than this particular picture. And this is a picture actually that was shared by a student in Misha Lukin's group. And she took this picture at the RMV, the Registry of Motor Vehicles, the most mundane of places on the planet, right? And you see a TV screen which is supposed to show people who are sitting bored, waiting for their turn to appear. Someone took the effort and thought that this piece of news was interesting enough to all the bored people sitting there that they made a slide and put it on that screen. How cool is that, right? So quantum computing seems to be everywhere. But not everyone actually understands what it's about, how it works. And so that's sort of where this tutorial essentially is. I hope that by the end of this tutorial, you have a better appreciation for what quantum computing is, how it works, and so on. So I'm going to start with classical computing. Talk very briefly about the two fundamental building blocks of a computer. And that's essentially how we represent information in the form of some physical state, and how we can manipulate or transform that information in some useful way. And of course, what I'm talking about are bits and gates. So the way you can encode information is through any physical system that can be in two distinct states, right? And there are lots of examples of states like these. You could have a toggle switch where the information is encoded in whether the switch is up or down, a punched tape, whether there exists or not exists a hole, a vacuum tube, whether it's in a conducting state or a non-conducting state. But our modern encoding of information is a transistor. And here's a picture of IBM's recent 2 nanometer gate-all-around transistor. And this, I want to emphasize that designing and fabricating something like this absolutely requires a deep understanding of quantum mechanics. Whether it's understanding the semiconductor band structure, understanding the transport of electrons through the channel, understanding electron tunneling through the oxide layer, which is really, really, just a few atomic layers thin. All of that really does require quantum mechanics. So here we are. We have our modern classical computing bit. And let's take this and abstract it a little bit. Many of you, perhaps most of you, are familiar with what a transistor is. It's basically a 3-terminal device. There's a gate, which is typically the input in this transistor. There's a source and a drain. The source can be connected to a battery. And if the voltage on the input is low, there's the channel between the source and the drain does not conduct. And we call this the off state of the transistor, right? Or zero. And we can denote the zero as a vector, shown here. Now, for classical computing, vectors aren't necessary, but they can be useful. And for anyone who comes from a physics background, knows that vectors can be denoted using the Dirac notation. That's the strange-looking brackets surrounding the zero. And if you don't know what this is, it doesn't really matter. But it's just another way to represent vectors mathematically. And in the Dirac notation, this is called a ket. So we have this ket 0, which can denote our off state. Now, the other end is that we apply a high voltage at the input. And what that does, it opens the channel between the source and the drain, and allows current to flow to the output. And we call this the on state of our transistor, or ket 1. So in short, that's essentially how information is encoded on our modern computers. How do we now transform this? How do we make something useful out of it? Well, the simplest way to transform this information is to take that one bit and flip it or invert it. This is the so-called NOT operation. And it's kind of straightforward to conceive how you could do this with a transistor. The easiest way one can imagine is you take your output, move it to the source side, and you ground the drain terminal. Now, if you have a 0 at the input, our channel is closed, and current flows directly to the output, giving you a 1 at the output. This can actually be represented as a matrix operating on our column vector, shown here. And in Dirac notation, you might see this denoted as follows. Again, you don't have to worry about the mathematics if you aren't familiar with it. But those who are familiar with this kind of notation might see that what I'm trying to do here is to use similar notation that's used for denoting qubits and operations on qubits. Now, if I apply a 1 at the output, our channel starts conducting. Current would rather flow through the channel into the ground, and as a result, our output is 0. And again, we can write it in our matrix representation. What if we have 2 bits? Well, if we have 2 bits, we have 4 possible states that our 2 bits can be in, denoted here. And we can also write these 4 states as column vectors, like we did for our single bits. And here's where perhaps you'll start noticing why this vector notation comes in handy, is we can create these 2-bit states simply by multiplying our single-bit states. And again, we can denote the same thing using our Dirac notation. Again, if it doesn't look familiar, don't worry about it. If it is familiar, the reason I bring it up is so that you can see the connection later on with the way qubits are denoted. What can we do with 2 bits? Well, we can do something like an AND operation. Again, it's very straightforward to visualize or conceive of how that can be done. We simply connect our 2 bits together. Now, if we connect the 2 transistors in series and I want a 1 at the output, the only way I can get that 1 is if both these channels conduct, allow current to go from the source to the output. And the only way both these channels would conduct is if I have a 1 on both the inputs, right? So that's the one and only way to get a 1 at the output in this configuration. Any other combination means that one or both of the channels are closed and current cannot go to the output and results in a 0. So AND operation, straightforward. We can actually take the next step, combine our NOT and AND gates in what is known as a NAND gate. Again, I won't go through the logic of how this NAND gate works, but suffice to say that the reason I actually went through the trouble of walking you through this is NAND gates are special. And NAND gates form what is known as a functionally complete set. And what that means is that you can implement any Boolean logic simply as a sequence of a bunch of NAND gates. So any logic you can conceive of, you can dream up of, you can implement using a bunch of NAND gates. So that's really at the heart of what a classical computer is. It's a whole bunch of bits, a whole bunch of transistors, billions and billions of them, all connected in ways that make transforming those bits of information in a useful way possible. All of this done billions and billions of times makes possible the magic of modern computing, right? So I made a point to emphasize that this is all of this is possible because of our deep understanding of quantum theory. So what makes quantum computers quantum? What's so special? What's different about quantum computers? I like this definition by David Mermin in his words from his book, Quantum Computer Science. A quantum computer is one whose operation exploits certain very special features of quantum theory. So the real emphasis is on these certain very special features, right? And I'm sure most of you must have heard of this. What I'm actually talking about is these features of superposition and entanglement. So the rest of this tutorial will try to understand how superposition and entanglement makes quantum computing different, perhaps special, and try to understand how all of this is put together. So we made a classical computer by taking bits, transforming them by using gates. Presumably, we could do the same. What if we encode information in a quantum physical system? And what if we find some way to then transform that information using, let's say, quantum gates? Would we build a quantum computer? And turns out that's in fact, it does work. And that's essentially how a quantum computer is built. So let's walk through both of these building blocks of a quantum computer. So quantum bits, qubits, are basically nothing but a quantum physical system that can exist in two distinct states, our states 0 and 1. And I'm sure you can think of many different examples of quantum states that have very distinct possibilities. The most obvious one is spin. I'm sure all of you know spin is quantized. It's a purely quantum property. And maybe a brief aside here, visualizing or representing quantum systems can be challenging. And so I took the easy way out here. And what I'm going to show is basically results from some very famous papers, as opposed to trying to make up some cartoon that ends up being wrong. So this is the famous result from the really famous Stern-Gerlach paper, which was the first experimental demonstration of the quantization of electron spin. And I don't know if you see it here, but this little split in this vertical line, that was what Stern and Gerlach used to calculate the quantized angular momentum of an electron. It's incredible how this experiment was done all the way back in 1922 with really rudimentary experimental apparatus. Yeah. Another example is to encode information onto discrete energy levels, whether it's between a ground state and an excited energy state. And this here, I show this as an example, the really detailed analysis of the hydrogen spectrum done by Theodore Lyman, in fact, right here at Harvard. Actually, the building right next to the one that we are in is named after him, and I think the funds for that building were actually raised by him. We could also encode information in energy levels of engineered systems. These could be quantum dots, these could be superconducting Josephson junctions. And this figure here actually is the first demonstration of the quantized energy levels that exist in superconducting Josephson junctions. And you'll notice all of this work is really, really old. Hydrogen spectrum, 1906. Electron spin, 1922. Josephson junctions, 1985. So none of this is really brand new work. It's just the big difference is that we are now able to use these results and control them in a way that makes us do something useful out of them. So going back, qubits are basically nothing but quantum physical systems where we can encode information in their distinct states. But here's the kicker. Any quantum physical system that can exist in distinct states can also exist in the superposition of those distinct states. And what that means is that we can have a state which is basically a linear superposition of those two distinct states. Now, why is that and how is that possible? Those are not easy questions to answer, but what we know for a fact is that superposition does exist. Quantum theory tells us so, and all our experimental evidence so far shows that that's true. Okay, quantum superposition happens. Our qubits can exist in some kind of weird superposition. Can we actually measure it? Well, it turns out no. And what happens is if we try to measure a state that's in superposition, it immediately collapses onto one of these two basis states. And all we can actually measure is the probability with which we obtain one or the other state. So again, why does that happen? How does that happen? Those are not questions, those very often tend into philosophical discussions, and it's a whole other story. But in the words of Paul Dirac, the principle of superposition is the most fundamental and drastic of the laws of quantum mechanics. So we know that this happens. Why or how, not something that we really are worried about. All right, so let's take that and abstract out the qubits a little bit more. So we have our qubits that can exist in two distinct states. We call these our computational basis states. But they can also exist in a superposition, which is a linear combination of our basis states. Now, these coefficients of the linear combination, they happen to be complex numbers, and we call them complex amplitudes or probability amplitudes. And we just discussed how nature actually hides superposition. We cannot measure a superposition state. If we try to do that, that superposition state collapses onto one of the two basis states. And all we can actually measure is the probability of ending up in one of those two states. And the fact that these probabilities are related to these coefficients of linear superposition give us what is known as a normalization condition. Again, if you have not seen this math, it doesn't really matter for what we're going to discuss, but this is mainly there for completeness. What if we have two qubits? Well, we could now write down our four computational basis states, but then we could also have a superposition of these four basis states. And again, if according to our measurement postulate, what we end up with is a normalization condition that combines all these four probability amplitudes or complex amplitudes. So this superposition really is at the heart of quantum parallelism. When you hear people say quantum computers can solve problems exponentially faster than classical computers, what people mean is this idea of quantum parallelism. And this is kind of how it arises is, so if you have one bit, that one bit can exist either as a 0 or a 1 at any given time. And so at any given time, that one bit contains one piece of information. But if you have a qubit, that one single qubit can also exist in a superposition. And as a result, at any given time, we can encode two pieces of information on that one qubit. If we have two of each, again, four possibilities, but for the classical 2 bits, at any given time, we only have two pieces of information, whereas with qubits, due to superposition, we now are able to process or encode 4 pieces of information. You can probably see how this is scaling up. So if we scale to n bits and n qubits, it scales linearly for bits and exponentially for qubits. And that's really at the heart of quantum parallelism. Now, exponential scaling really becomes mind-boggling, right? You can sort of see, even if n is a relatively small number, like 500, the number 2 to the n becomes incredibly large. In fact, you might have heard this number thrown about 2 to the 500 is greater than the number of particles in the observable universe. And you could probably start imagining, well, if I have 500 qubits and they are all in superposition, the amount of information that they can encode is just incredibly large, right? We cannot conceive of what that actually means. And that's kind of what quantum parallelism actually means. But hold on, we just said, well, we can't really measure superposition. Nature hides it. We try to measure, everything collapses. So what's actually going on? Is this even useful? And it turns out that it can be useful. And in fact, if we are able to control and controllably, precisely evolve a closed quantum system without taking any measurements, we can let nature take care of all this hidden information without us having to measure and reveal all of it to us. So this really is at the heart of quantum computing, understanding how to let nature evolve and take care of all this information while we make sure that that system is not disturbed. That's really the heart of quantum computing, understanding how to do that. And that requires understanding not just the science of how quantum mechanics works, but also the technology behind making sure that we can create a closed system, controllably evolve it, and allow nature to do something useful with it. So just to quickly summarize, we talked about qubits, which are nothing but quantum physical systems which can encode information in their distinct states. These states can be in superposition, which enables this whole exciting thing about quantum parallelism and understanding how to keep the system in superposition really is what quantum computing is all about. So how do we do that? How do we evolve our qubits? That's where quantum gates come in. And so we'll talk briefly about what quantum gates are and how we can use them to start transforming our qubits in a way that don't require a measurement. So just like with classical bits, the easiest operation you can do with one qubit is to invert it, to flip it. And that's what a NOT quantum gate does, also known as an X gate. And there's a matrix representation of that gate. And all it really does is if we apply it to, let's say, the 0 state, it will flip it to the 1 state and vice versa. What if we apply it to a superposition? What we'll see is that the gate actually acts linearly. And essentially, the operation it does is to exchange the coefficients of these computational basis states. So the important thing to note here is that quantum gates act linearly and are reversible. And mathematically, what this translates to is this property called unitarity. And what this means is that if you can write a matrix, take its complex conjugate transpose and multiply it with itself, if you get an identity matrix, then that matrix is a unitary matrix. And amazingly, that really is the only constraint on quantum gates. And so you can imagine any matrix, if it happens to be a unitary matrix, then you can create a quantum gate that takes that matrix and creates an operation out of it. So very briefly, how would one implement a NOT gate? So for example, if our qubit is a spin, if we encode the spin up as the 0 state and spin down as the 1 state, we can use a magnetic field to flip the spin from 0 to 1, right? So our NOT gate essentially is just the application of a very precisely timed, let's say, magnetic field. Here's another prototypical quantum gate. And there is really no analog to this particular gate in classical computing. And this is called the Hadamard gate or the H gate. And again, I show you the matrix representation, but again, understanding what that matrix does is not necessarily important right now. But if you take that matrix and apply it or multiply it to our computational basis states, what you end up seeing is that it generates a uniform superposition. So you can perhaps now tell why this has no classical analog. And so Hadamard gate actually generates superposition. How does this actually work? How can one implement a Hadamard gate? Well, the details of the implementation depend very much on the physical system of qubits that you're using. And I'm pretty sure you'll hear a lot more about implementations and various technologies in the next tutorial by Giulia Samaghini. But let me give you a very generic explanation. Let's say we have a qubit that's encoded in the energy levels of a quantum state. Now, this quantum state could be an atom, it could be a molecule, it could be an ion, it could be a quantum dot, it could be a superconducting Josephson junction. The details make the implementation very different. But in general, if we zoom out, here's a qubit which has information encoded in energy states. We can push this system from its ground state to its excited state by applying some sort of coherent light pulse. Now, I use the term light pulse very broadly. If these are atoms or molecules or ions, the light pulse is basically a pulse of a laser. If these are superconducting qubits, Josephson junctions, our light pulse is basically a microwave pulse. And the way we would actually apply this light pulse is by connecting various waveguides and so on. So the technology can be vastly different, but the idea is kind of similar. You apply a coherent light pulse, push the system to an excited state. Now, once the system is in the excited state, it can, after a little while, relax back into a ground state, right? And as long as our pulse is turned on, the system can again be pushed to an excited state, and it can again relax back to a ground state. And in fact, what we see is that the system oscillates between the excited state and the ground state. And these are called Rabi oscillations. Now, it turns out that when the system is performing these Rabi oscillations, the probability of finding the system in either the ground state or the excited state depends on the frequency of these oscillations. And the really cool thing is that we can actually tune the frequency of these oscillations by a precisely tuned coherent light pulse. So by using a pulse of just the right frequency, just the right duration, intensity, and so on, we can tune the frequency of these Rabi oscillations and therefore tune the superposition of the system to be in the ground and excited states. So that's really the essence of how one can create a Hadamard gate. Again, the details and the technology of the implementation can be vastly different depending on the physical system. Here's an example of when we have two qubits. This two-qubit gate is called the controlled NOT gate. And I show you the matrix representation here. But here's how it actually works. We have two qubits. Let's call one qubit our control qubit, qubit C. And the other qubit, we call it our target qubit, qubit T. If qubit C is 1 or 0, we do nothing. We leave the system as is. Our target qubit is as it was. If our control qubit is 1, we apply the inversion operation, the NOT operation on the target qubit. And together, this can be written as the addition modulo 2 of the target and the control qubit. Now, here's a really interesting gate. If you think about it, what we're doing is some sort of conditional operation, right? Depending on the value of our control qubit, we're doing some operation on our target qubit. So how can we do that without measuring what the control qubit is? Because as soon as we measure something, we know that our state changes and all those strange collapses happen. So how is a CNOT actually implemented? And again, the details vary a lot based on what technology we use. But at the heart of the idea is really we have two qubits. And the magic of this conditional operation comes from a coupling between the two qubits. Now, what is this coupling? It varies by what the qubits are. For instance, if these qubits are neutral atoms, then the coupling is basically a dipole-dipole interaction created by what's called Rydberg blockade. And I'm sure Julia will talk a lot more about this. If these are superconducting qubits, it could be the capacitive or inductive coupling between the tunneling junctions, the Josephson junctions. So we can generate some kind of coupling. Can we actually control that coupling? And turns out yes, and in fact it's the same process really. We can use some kind of coherent light pulse, and again light used very broadly. It could be a laser, it could be a microwave, but by precisely tuning that light pulse, by tuning the shape of that pulse, we can control how these qubits are coupled and therefore perform this conditional operation. So the reason I bring up these few specific gates is that just like in the case with NAND gates, the CNOT combined with the Hadamard and some other single qubit gate actually form a functionally complete set. And that really is incredible. What that means is we can perform any qubit logic just by breaking it down in a sequence of CNOT and a bunch of single qubit operations. So even though any unitary matrix can in principle be a quantum gate, and one can imagine that leaves us with infinite possibilities, the technological implementation really requires us to implement just a few small number of gates, a CNOT gate and a few kinds of single qubit operations. And so what that really says is that once we have a way to encode information onto quantum physical states, once we can control their superposition, we can in fact transform them by using quantum gates. And we don't require that many different kinds of quantum transformations to do useful logic with quantum gates. Now, one of the earliest programmable machines was this complicated apparatus called the Jacquard loom. I'm pretty sure that's not how you pronounce the name, it's French. But this is an apparatus, this is a machine from the early 1800s. And this machine was used to program or programmably weave patterns onto fabric. And this was really the first representation or use of physical bits to represent information. And Jacquard used the system of punched cards. And if I am to believe Wikipedia, Charles Babbage got his idea of using punched card systems for his analytical machine from Jacquard. And it took us roughly 200 years to get to our magical current state of modern computing. We are really at a stage where we are starting to build programmable quantum processors, quantum machines. And the question really is, how long is it going to take us to get to the magic of quantum computing? And honestly, the bigger question is, what is this modern magic of quantum computing even look like? I'm not sure we actually have these answers, but what I expect is that throughout this conference, hopefully you'll hear talks that give you some indication of where we are heading and why this field is so exciting. There's lots of potential, lots of directions that we could possibly go in, and perhaps lots of magic to be done. What that would look like, that really depends on where we go. So far, I've only talked about superposition. Superposition enables quantum parallelism. Great. What about entanglement? Well, let's very briefly talk about what entanglement is, and then we can maybe discuss how it's actually useful. So let's say we have two qubits. I have a qubit 1 and qubit 2. We can write down its combined 2-qubit state by simply multiplying the single qubit states, right? And earlier when I showed this multiplication, I had sort of omitted this multiplication operator. There's no real convention. Sometimes people keep it, sometimes people omit it. What it actually denotes is a tensor product of vectors. So in general, we could have two qubits in superposition, and we can again write down their general 2-qubit state by taking the tensor product of these two single qubit superposition states. It gives us this complicated looking expression. But essentially what we have done is simply taken the multiplication of the single qubit vectors. We also discussed that if we had just one qubit and in a superposition state and we are to measure it, it collapses to one of the two computational basis states, and the probability is given by its complex amplitudes, right? But what if we have this 2-qubit state and we were to measure just one qubit? What would happen in that situation? Well, let's say we try to measure qubit 1, right? What would happen is still the same thing. That qubit 1 would still collapse to either one of its basis states, either 0 or 1, but this time with a slightly different probability given by these terms over here. Now, let's say we actually do this measurement and our qubit 1 is found to be in state 0. Our combined 2-qubit state immediately then transforms into this new 2-qubit state. And why is that? Because now we know for certain that qubit 1 is in state 0. So the only possible superposition is the one that I show you here. And this additional factor in the denominator now comes from the normalization condition. So we measured qubit 1, we found its state. But if I want to know what state qubit 2 is in, I'll have to do one more measurement because qubit 2 can still be in a superposition, right? So I would need another measurement to determine the state of qubit 2. Now, let's see what happens if we have this particular superposition state. So here I have sort of a uniform superposition between the 0, 0 and 1, 1 states. If I compare this to the general 2-qubit state that we wrote down earlier, what we would find is that A1, A2 and B1, B2 have to be 1 over square root of 2. And then A1, B2, A2, B1 have to be 0, right? It's just directly comparing my 2-qubit state with this general state. But if you look at it more carefully, what you'll find is that there's basically no possible value of A1, A2, B1, B2 that satisfies this condition mathematically. This just does not exist any possible way that we can satisfy this. So what that is telling us is for this particular state, for some reason, we cannot write it as a product of two individual states. And that really is what entangled states are. They are multi-qubit states that cannot be factored into individual qubit states. And this particular state I show here is one of the 4 famous Bell states, also known as EPR states for Einstein, Podolsky, Rosen. So clearly there's something special with this, this state that cannot be factored into individual qubit states. So let's look at what's special about this particular state. So say I have created the state and I want to measure qubit 1, just like we did before. Now if I measure qubit 1, what would happen? Just like before, our qubit 1 would collapse onto either 0 or 1. Now this time with 50% probability. Right? That's how the state is written down. That's what our normalization condition gives us. But if I do this measurement and if I find my qubit 1 to be in the state 0, my 2-qubit state immediately transforms to the 0, 0 state because there is no other possible superposition where qubit 1 is in state 0. And here's where that something special really has happened. So by doing just this one measurement, we now immediately know what the state of the second qubit is, right? And that's really the magic, or I mean, magic is not really a good word to use here, but that's what is special about entanglement and why it is a powerful resource for quantum computing. So you'd often hear this phrase that entanglement is a resource for quantum computing. And what people mean is really this idea that entanglement allows you to do something that would require one less measurement. You know? And maybe I can give you one example of how this could be useful. Any physical system is bound to have errors, right? You can imagine bits flipping just randomly from noise, or gates transforming but creating some kind of error or noise and so on. And the same, of course, happens to quantum systems. Now, the big difference is in classical systems, it's very easy to correct these errors. You can take your classical bit, make a copy of it, every once in a while measure the original bit, make sure that it's the same as its copy. If it's the same, we're done. If not, we can just do some kind of operation on the original bit and we have corrected the error. But this is not possible for qubits, and this principle is called the no cloning theorem, and it stems from the idea that if we are to measure a qubit, its state actually changes due to that measurement. But now what entanglement allows you to do is to spread this information out onto multiple qubits and sort of, in a way, to go around this no cloning theorem. And this is at the heart of the famous Shor's error correcting code, which Peter Shor first proposed in 1995. And he came up with the idea of encoding information on 9 entangled physical qubits to create 1 logical qubits. And the idea was that these entangled qubits would then be able to protect against both bit flip and phase flip errors. And essentially the idea being that these entangled bits could be indirectly measured by some other ancilla qubit, where the measurement is actually performed on the ancilla as opposed to the logical qubit. So great. Now, what that actually means is superposition, allowed us, or in principle allowed us, this huge potential of quantum parallelism. But entanglement is actually what makes this practical. It allows us to actually correct for errors, and in principle gives us maybe something tangible that we can do with quantum parallelism. That's great. Is this something we can actually create? Can we create entangled states? And it turns out we can, and we could actually use our quantum gates. So the easiest, the Bell state that we just talked about, we can create that Bell state simply by using a Hadamard operation on 1 qubit followed by a CNOT operation on 2 qubits. And so in principle, we can create these entangled states, again, simply by a combination of our CNOT and a bunch of single qubit gates. And again, to emphasize this point, the real potential, the incredible excitement around quantum computing comes from these two ideas that superposition could potentially allow us this huge speed up from quantum parallelism, and entanglement actually makes this technologically possible, perhaps. And really, the heart of quantum computing, like I said, is understanding how to maintain that superposition perhaps by the use of entanglement and correcting for errors. There is another often noted use of entanglement, which is this idea of super dense coding, and I won't go into the details of it. But what it essentially allows us to do is to double the classical information carrying capacity of a communication channel. And one can imagine quantum networks in the future that have the fastest streaming possible, and I'm sure you'll hear more exciting things from Neil about quantum networks. But the reason I bring this up is so that I can actually go full circle back to this image I showed you before. Our mundane registry of motor vehicles TV screen, and I don't know if you can actually read the text on that TV screen. It says, Amazon and Harvard University have created a quantum network that transmitted an entangled photon from one quantum computer to another over 35 kilometers of fiber optic cable. Now, I hope that if you happen to see this kind of news, you'll have a better appreciation for what's involved and how this actually could potentially be done. And this news actually comes from this particular paper that was recently published. And I show this not to actually talk about the paper, but to point out this fact. If you look at these last 4 authors on the paper, we have Misha Lukin, professor in physics, Marco Lonchar, professor in electrical engineering, both of whom you'll actually hear from later in this conference. Hangkun Park, professor in chemistry, Mihir Bhaskar, group leader in Amazon. And so this advance in quantum computing is really only possible by bringing together people from all these different fields. And that's really my final message to you, is that the future of quantum computing really requires all these different fields, people from all these different fields to work together and advance various pathways forward. So no matter what field you're coming from, there are ways that you can contribute to quantum computing and perhaps in your lifetime see what the magic of quantum computing actually looks like. So with that, I'll stop, and I'll happily take any questions. And thank you for paying attention.
We actually have time for a few questions. Question?
So you talked about Okay, I was saying, so you talked about like errors in bits and with classical computing and how sometimes they flip and things like that. What are some errors that qubits can take up?
That's a great question.
Yeah.
Like I mentioned, qubits essentially can exist in superposition, right? You can have a superposition of the 0 and 1 state. Now, there can exist two kinds of errors in qubits as opposed to just like the single bit that can just randomly flip. In qubits, you can have the bit flip error, which basically means that our computational basis state essentially flips. If it's a 0, it might flip to 1, and so on. But there is an additional, a new kind of error, which is called a phase flip error. And that kind of error essentially means that the complex amplitudes that are involved in the superposition essentially gain some kind of phase, additional phase. And that's an error that does not exist in classical computing. It's inherent to something that results in, that's due to superposition, and due to the fact that these coefficients of superposition are complex numbers.
Okay, and so does that mean that the additional phase could possibly be a good thing?
Well, if it's an error, it's not a good thing. So
it's noise, right?
So exactly. So there could be thermal fluctuations. There could be, noise in the way we are pushing the system from one state to another. All of these could lead to some additional phase. Now, the phase actually is important because it is important in how our system evolves. But any noise in that phase, of course, is detrimental. And it's important to not just correct the flipping of these basis states, but also that noise in the phase.
Yeah, kind of an interesting way you can think about it physically is Nishant described a little bit earlier about how you could create a state by generating a Rabi oscillation between a ground state and an excited state. If there's some external factor that modulates either the ground state a little bit or the excited state a little bit, that's your phase noise.
Yeah.
Okay, thank you so much for the talk. So you mentioned that entangled states are states that cannot be factorized into two different states. I was wondering if there is there any conclusion we can derive in terms of the unitary transformations that lead to entangled state? Can they also not be factorized? Do they belong to a particular class of unitary transformation?
So that's a good question. I'm not so sure about if there's a sub system or a subset of unitary matrices that correspond to operations that lead to entanglement. I think maybe I can look into it and find you later during the conference.
So you mentioned that the classical computers are traditionally digital, meaning that the bit states are 0 and 1. Would it be correct to think of these quantum computers as analog computers, meaning that the bit states are a percentage of 0 and 1?
Yeah, that's a great question. There are a lot of parallels between analog computing and quantum computing, but the big difference really is even if we create a classical system that is based on our states being analog, not digital, the certain special features that come from superposition entanglement do not exist in those classical analog systems. So one could imagine a superposition with analog states, but entanglement really is a purely quantum phenomenon. And even with superposition, the idea that our information is encoded in these complex amplitudes, and the measurement postulate that one can evolve a superposed system while not caring about what the exact superposition states are. It's a purely quantum phenomenon.
Hi, great talk, by the way. You mentioned that all quantum gates are unitary, therefore reversible. I know, because I work in quantum photonics, some methods that allow you to have entangled states of photons, spontaneous parametric processes like SPDC or four-wave mixing. I wonder if there is physically a process that allows you to de-entangle some photon states. If it is reversible, then can we sort of go back from entanglement to separate independent states in photons, say? I know mathematically there is some de-entanglement theorems, but is it physically possible?
As far as I understand, I think by definition, entangled states are ones that cannot be factored into the individual quantum states. Now, I think what your question, if I rephrase your question, I think what you're asking is one could imagine creating these entangled states using some kind of unitary transformation, right? And we said, by definition, unitary transforms, the fact that something is unitary means that it's reversible. So the question is whether once we do the transform, we can go back to the...
Yeah, like Hadamard photo by C naught gives you entanglement, right? I think in a circuit it is possible to write the inverse of C naught and the inverse of Hadamard, and then you have the entangled states. But what about physically? What would that mean physically?
It's hard to imagine you can do that with it. That sounds like a free lunch.
Yeah, I'm not sure what that would mean physically. I can't think of an implementation where you could do an inverse of those to get back a single qubit state.
Hello, thank you. Brady from Howard University. From an electrical engineering standpoint, where do you see the hand-in-hand evolution of our physical systems in terms of like being able to handle this kind of possibilities? Because from what I'm understanding is with something like this, you can basically have less and more. But are we really investing or pushing in the direction of being able to hold that physically into a system per se?
So I'm sorry, I didn't hear the first part of your question.
So yeah, it's really just like, where do you see, looking at like the electrical engineering standpoint of it, like where do you see like the evolution of our physical technologies to be able to like?
Kind of asking, when are we going to build something?
Yeah.
So like I said, we are starting to build these systems. There exist, I think every year or so, there's a new hardware platform that someone creates onto which you can encode these qubits. We have superconducting qubits, we have neutral atoms, we have molecules, ions, quantum dots, we have defect states. There was one, again, a very old idea, but I recently came across it, is one can float helium ions on like, not helium, one can float electrons on superfluid helium and encode information on the spin of these electrons. So a lot of these technologies have been shown to be practical, but we really are at a stage where we just started scratching the surface of how we can be very controllable, very precise with these transformations. What is involved in taking these initial demonstrations of here, I can create a qubit, to here, now I have a whole bunch of qubits that can be controllably, manipulated. So in other words, scaling from few qubits to many qubits is a big challenge. And I'm sure you'll hear a lot about that in Julia's talk. The other really cutting edge aspect of quantum computing is figuring out how to actually do error correction. I briefly mentioned the Shor error correction code. There are many other proposals for ways to correct for errors. But then again, technologically implementing that, doing that controllably, repeatedly, they are all challenges. And a lot of these challenges are where electrical engineers are critical. Being able to, again, maintain these superposition state in devices, probing or measuring states in these platforms. All of that requires a lot of technology.
So I'll sneak in one comment because I have a similar complaint that you have, in that I think we've gotten to the point where we could describe complete sets of elements that give rise to a complete set of logic operations in these systems. But then, so I grew up, kind of in the 80s, and in the 80s you could walk down the street to Radio Shack and you could buy little chips to wire up logic circuits. And so I asked the question, well, why haven't somebody built like a half adder or something that looks like an op amp, right? I mean, so it's not clear to me why. I guess because it's not easy, right? But it would be interesting as a way of evolving the platform if people just made simple logic circuits, maybe a little more complex than they do now, as a way of walking the path.
A quick thing about that. So in principle, you could actually create a half adder or a full adder using a bunch of quantum gates. The question is really, is that a useful thing to do? And is that actually using the ideas of superposition? Does that actually give us any advantage over classical computing? And those are questions I think that technically remain to be answered. What sorts of algorithms actually have an advantage over classical computers? So, in principle, possible, but whether it's useful or not, those are things to be considered.
Thank you.